We know that graphs are related to equations, and we know that if we make a change in an equation, it'll result in a change in the graph. Well, it's also the case that we can imagine graphs of certain kinds of equations. Now, we already know that with linear equations. If we think about a linear equation written in a certain form, that is, in the slope-intercept form, then we can imagine its behavior. We can imagine where it goes through the coordinate plane and how steep it is and that kind of thing. Well, we're going to extend that idea. We're going to consider some more complicated equations and more complicated graphs here. And it'll turn out that we'll be able to easily imagine these graphs, and we'll easily be able to imagine the changes in graphs as we make subtle changes to those equations. All right, let's begin with a rather degenerate quadratic equation. F of x is x squared. When we graph this, we write it in this form, y equals x squared. Here's a table of values associated with that equation. If I plot the points and construct the graph, I get this parabolic curve. Okay, now let's begin there. Let's make a little change. We're going to take the f of x is x squared, the x squared business, and subtract 3. We would write this then as y equals x squared minus 3. Here's a table of values associated with that equation. Now, just take a look at the table of values. It'll give us a pretty good idea of what's going to happen to the graph. Now, this column of x values is identical to this column of x values. But look at the y values here, 0, 1, 4, 9. Over here we have negative 3, negative 2, 1, and 6. Now if you compare these two, you'll notice that for each y value, these are 3 smaller than those were. Now think about y as a vertical distance. The vertical distances here are just 3 smaller across the board than all of the vertical distances over there. So it'll be no wonder that the graph associated with this equation is just 3 down from the previous graph. Now we can think of it conceptually like this as well, that again, y represents vertical distances. So the y equals x squared that we had over there, you see this is just a set of vertical distances, you see, given by or described by this, and now this y is those vertical distances we had over there here minus 3. So subtract 3 for all of those, and the graph falls 3 on the coordinate plane. All right, I'm kind of over-explaining the situation, but it's a very important idea for a particular shift in the graph. Now, if I plot these points, let's see, 0 goes to negative 3, and then plus or minus 1 goes to negative 2, and then plus or minus 2 goes to 1, and then plus or minus 3 goes to 6. All right. So this graph sort of predictably looks like this. It's a shift downward. Now, here's what I want you to understand conceptually, that we have a prevailing operation here, squaring. And with our other families of equations in their graphs, we're going to have a prevailing operation. We're going to be talking about absolute value and cubing and square rooting. Okay, so for each degenerate kind of equation and graph, we have a prevailing operation. And what we should notice here is that we're adding or subtracting, in this case subtracting, after we perform the prevailing operation. That is, we square x and then we subtract 3. So the graph falls 3. If we were adding after the prevailing operation of squaring, then the graph would rise on the coordinate plane for the same reasons that we talked about here. Now let's talk about the notion of adding or subtracting before performing the prevailing operation. That is, suppose we consider an h function which is x minus 3, then square. You see, so we're subtracting 3 before performing the squaring. Okay, we would use this form to make a table of values. This turns out to be the table. I'm not using the plus minus here because we don't have an x distinct, a little x squared, but giving us the same value for plus or minus values that would be squared. Okay, anyway, let's plot these points and just see what happens. 0 goes to 9. 1 to 4. 2 to 1. 3 to 0. 4 to 1. 5 to 4. 6 to 9. Graph looks like this. Now notice the shift. And all we're talking about so far is shifts that are up, down, left, and right. Notice that this shift from our basic graph, we're actually shifting this graph 3 units to the right. Well, the 3 we can kind of see here by the nature of the equation. You see, we see x minus 3, but gee, we're shifting in a direction we probably don't expect. Let me tell you why that happens, and I'll tell you how you're going to remember this, how to recall it later. What's happening is that the squaring of real numbers results in a parabolic curve. All right, now think about that on this coordinate plane. All right, so here we have real numbers, and the squaring operation results in a parabolic curve. Now let's suppose that before we even perform the operation of squaring to give us this parabolic curve, we take our entire coordinate plane, our x-axis, and we shift it to the left. That's the x minus 3. We take our real numbers and subtract 3. Now what happens? Well, the position where the y-axis was here shifts over 1, 2, 3 places. So now here is our y-axis, you see. Our y-axis comes over here. And the graph appears to have moved to the right when in fact the coordinate plane moved to the left before we squared to give us this behavior. So that's the idea, that really it's not so much the graph shifting left and right, it's the idea that the coordinate plane has shifted and the graph has stayed where it was supposed to be in the first place. All right, the way you'll remember it though is this, that if we are adding or subtracting after a prevailing operation, then the movement of the graph is up and down. If we add or subtract, as is the case here, before the prevailing operation, the graph moves left or right. And that's all there is to it. And it moves in a direction we don't expect. If we see x minus 3, then the graph moves plus 3 on the coordinate plane. Now, it's handy sometimes in thinking about shifts like this to think about one point, one critical point on the graph shifting, and all the other points follow. The point that's nice to consider here with parabolas is the vertex, the topmost point or the bottommost point. It happens to be the point, in this case, that falls at the origin. So we think about that point moving somewhere on the graph, and everything else follows, and we can construct the graph or sketch a graph. Now, let's take a double shift here. J of x is x plus 2 squared plus 3. All right, 2 shifts. Now, if we're shifting before the prevailing operation, then we shift left and right. If we add or subtract after the prevailing operation, then we shift up and down. All right, so let's think about what's going on here. This adding of 2 happens before the prevailing operation, so we're going to shift left or right in a direction we don't expect. Now I'm thinking about the position of the vertex only. So the vertex will move to the left from here. On our basic graph, you see, you think about it compared to the basic graph, the vertex shifts 2 places over this way. All right, that's where it is according to this. Then plus 3. Plus 3 after the prevailing operation sends the graph up the coordinate plane 3 places, so the graph then will look like this. All right. These kinds of transformations are called rigid transformations when we shift left, right, up, down. There are a couple of other rigid transformations, and they are reflections. We can reflect like this, or we can reflect like this. Now, an example of a reflection like this for this one is like this. Come back over here and consider what would happen if I constructed, if I constructed the graph of y equals the negative of x squared. You see, these are just vertical distances, and these are the negatives of those vertical distances. So the graph then will have this appearance. See, the graph will look like this. It'll be this basic graph, but it will have reflected in our x-axis. Now, the reflection this way is not easy to see with parabolas because there's symmetry about the y-axis. So when it reflects this way, it looks like exactly the same graph. So it's not very worthwhile to think about. But it happens like this. If I constructed the graph of negative x squared, then it would result in the same parabolic curve. But this, we can think of this, the graph of this, as just the reflection in the y-axis of that. Now, let me generalize this situation even further. A lot of times we see these kinds of transformations occur and indicate them using function notation. That if this is f of x, then what would this be? Now let me slide down. I want to slide this down just to have a little more room. How would we describe this in function notation? You see, this is nothing but the negative of f of x. Because after all, f of x is x squared. So the negative of f of x is negative x squared. You see? And this is, well, gee, how does this differ from that? You see, it is in the f function we have replaced x with negative x. Well, that's just f of negative x. All right. Now, the emphasis here is that the negative of f of x will cause a reflection in the y-axis. We'll get this kind of reflection. F of negative x will give us this kind of reflection, a reflection in the y-axis. All right. Now let's go through this function notation idea over here, that it looks like g of x here was x squared minus 3, but notice how we can write this using function notation. The g of x is nothing but the f of x that we started with minus 3. You see, we take our basic function and we subtract 3. No wonder the graph moves down on the coordinate plane. Now over here, we are replacing the x with x minus 3. You see, so this is really nothing but f of x minus 3. And the graph ended up moving left or right in a direction we don't expect. It ends up moving plus 3 on the coordinate plane. All right, that's the idea. Now, so far now we have all these rigid transformations. We have left, right, up, down types of transformations. And we have reflections, which are also rigid transformations. We have reflection in the x-axis. We have reflection in the y-axis. There are other transformations that we want to talk about just briefly. And they're called non-rigid transformations because they actually change the form, the shape of the graph somewhat. They make the graph look, well, a little bit fatter or a little bit thinner. That's the idea. Now I can show those, well, rather than come over here, let's come over here. I want to consider those in just a moment because they'll be the result of what I talk about over here. Consider the idea of a y which is, let's say 1/3 x squared. Now 1/3 x squared. And this is equivalent to saying 1/3 f of x. But what does that mean? That these vertical distances are 1/3 those vertical distances. For every x value, these y values are going to be 1/3 as high as those y values. You see, that's the idea. So, gee, I have a pretty complicated looking graph up here, but I need to put in this graph, the graph of this one if I can. I'm going to take this rascal out and see if I can create some room. All right, let's see if we can do this right on top of this. Now, I'm looking at this graph, and I'm thinking all the vertical distances described here are just 1/3 as high as those. So for an x of 1, we had a vertical distance of 1, you see, on the basic graph. But now for this one, 1/3 x squared, it's 1/3 of that, just 1/3 as high. And for an x of 2, we had an f of x of 4, you see on the basic graph. 1/3 of that is about right here. And then for an x of 3, we went up to 9. 1/3 of that is 3. You see what's happening? That this graph is sort of fattening out because of this coefficient of 1/3. Same thing will happen over on the other side. So we'll get a graph that kind of looks like this. You see, it just kind of broadens it out a little bit. If it was 1/10, it would really lay down pretty much like that. Okay. So if we multiply by a coefficient that is between 0 and 1, it will cause this fattening idea. Actually, if we multiply by a number, a coefficient that is between -1 and 1. You see, it's the positive or negative ordinary everyday household fraction as a coefficient times the function. So it'll cause it to kind of lay down. Now, if it's negative, it'll cause the reflection to happen, but it'll still widen out as well. Okay, now what happens if the number turns out to be, let's say 4x squared? Well, a coefficient like 4 will just make all of the x values associated with y equals x squared, it'll make every one of them 4 times as high. You see? Just the vertical distances are 4 times as high. So when I talk about an x of 1 going to 1 in the basic graph, the x of 1 in the graph of this rascal will go up 1, 2, 3, 4. You see, and -1 will do the same thing. So that graph will kind of look like this. It look really thin. So it'll cause the graph to kind of thin out like this when you multiply by something that is greater than 1 or less than -1. All right, non-rigid transformations. Now let's put all the ideas together. There are other families of functions and graphs. If we think about a degenerate cubic function, f of x is x cubed, this is its graph. Now let's try to imagine the graph of h of x, which is 1/2 x minus 3 squared. Oops, I wanted to put x minus 3 cubed plus 2. Can we imagine this? I think so. Let's start like this, though. When you try to imagine these things, take your basic graph and then start making changes to it. All right, just this change, the x minus 3. Now, we're subtracting 3 before the prevailing operation, so that's a shift left and right. And it's in a direction we don't expect. We see -3, the shift is going to be to the right 3. Think of this point as a key point on this graph, and that point moves to the right 3. All right, here it is. Now the graph is right there. Okay, now what's 1/2 times that do to it? 1/2 of it, all those vertical distances are half as high. Whoa, that's going to cause it to kind of lay down a little bit. I'm going to overemphasize it like this. You see, it kind of lays down to the x-axis just a little bit. All right, now what's plus 2 do to it? Oh, plus 2 after the prevailing operation, that raises the graph 2 units on the coordinate plane. So this point comes up here, and now our graph, I want it to be a little bit lazy here and do like this. And I'm kind of overemphasizing the lazy part probably. Probably doesn't get this lazy. Okay, here's another one, absolute value function. The absolute value function, the degenerate form, the graph looks like this. Now, what if I construct the graph of this? Well, again, let's take it from the beginning, kind of like this. All right, here's our basic graph. Now, just analyze one part at a time. The prevailing operation is absolute value. So here we are adding 1 before taking the absolute value. When we add or subtract before taking absolute value, the shift is left or right in a direction we don't expect. We see +1, so it's going to move -1. So the graph moves to this position. -2. Let's take one of those ideas at a time. All right, let's see. 2 is going to move the y values up the coordinate plane a little faster, twice as high for every one of them. So the 2 business is going to do this. Going to make it be a little bit narrower v here. And then the negative is going to cause a reflection in the x-axis, and so it's going to look like this. And the +3 is going to move it up. So here we go. Up 1, 2, 3, moves up to this point, and looks about like that. Now you can verify all of this stuff using the graphing calculator. In fact, tell you what, let's take this degenerate square root function. K of x is the square root of x, and this is its graph. And let's examine aspects of transformations on the square root of x. I've entered a number of equations involving the square root of x or variations along that theme. Now notice that the equal sign is highlighted here but not highlighted here, and in having the no highlight will cause the graphs of these equations not to appear. I'll show you how to highlight them in just a little bit. But the graph of the square root of x is here, and it is as we would expect it to be.
By the way, the window setting is rather close. That is, we're getting a fairly close view of this graph because from the standard setting, I pressed zoom and then number 4 for decimal. But if you're following what I'm doing, that's how I got this kind of viewing rectangle. Go back to y equals, and we're going to pick up the next graph. I'm cursoring to the left and then down one. With the blinking icon on the equal sign, press enter, and it'll highlight that equal sign, and now we'll pick up both of these graphs. Before we see the graph, though, we might anticipate what we expect from the graph and the transformation. We notice that we have x plus 3 here, and the adding of 3 is occurring before the prevailing operation of square rooting. And we know that because of the existence of this parenthesis, which contains the x plus 3. All right, so we may expect the graph to move left or right in a direction we don't expect. We see plus 3. The graph should move to the left 3. So here's the original graph, and the transformed graph is to the left 3 from the original. Go back to y equals, and let's cursor down and to the left. Press enter to take this graph off screen, and go down and press enter here, and we'll put this one on screen. Now notice that this one is simply the square root of x and then minus 2. The subtraction of 2 is occurring after the prevailing operation of square rooting, so we would expect this graph to be the standard graph but down 2 on the coordinate plane. Let's see how it looks. Okay, there's the expected graph. Go back to y equals. Now this is all very predictable kinds of stuff, so let's press enter here, take that one off, and go to the next one. Now we're talking about a rather interesting shift for this particular graph. This one will shift in, well, let's think about it now, the negative of x plus 2. Well, the plus 2 will move the graph left or right in a direction we don't expect. It'll move to the left 2. But this negative will cause a reflection in the y-axis. So let's see, we ought to be shifted to the left 2, and we ought to be reflected in the y-axis. Let's see what happens. Oh, well, yes, we do. We have the reflection that we expected here, and we're shifted 2. All right, next graph. Pressing enter here, and we'll take that one off, and I'll highlight this one. Now let's see what we might expect. I'll tell you what let's do. Let's look at both of these graphs at the same time, because it's rather interesting to see how these differ from one another. Now notice that in this one we have the negative of x plus 2 under the radical, and it caused a reflection in the y-axis. And here the negative is before the prevailing operation, and the reflection will be in the x-axis. Let's see how they are the same or different from one another. There we go. Now that last one, this was the one that was the negative of the square root of x plus 2. Well, press y equals again, and let's take these two graphs off. Let's cursor down and press enter with the icon on this equal sign, and then enter with the icon on this equal sign, and press enter with the icon on this equal sign, and we'll access this last graph. Now let's see what we might expect. The negative sign here on x will cause the graph to reflect in the y-axis. This negative sign will cause the graph to reflect in the x-axis. Now the 2 will cause each vertical distance to be twice as far as they would be on the original graph. So the graph will look, well, let's see how it looks. Here's the original graph. There's kind of a double reflection now. The reflection in the x-axis, in the y-axis would have caused the graph to behave like this. The reflection in the x-axis would cause the graph to look something like this. And the 2 caused all of those vertical distances to just be twice as far down. Now to illustrate that, let's go back to y equals, and I'll enter a graph very similar to this one. The negative of the square root of negative x. Now, I just want to show you the difference between these two. This is the negative of the negative, the negative of the square root of negative x. And this is just negative 2 times the square root of negative x. That's what this one is. So it's like the multiplication of 2 is taking this vertical distance for that x value, and this vertical distance, just double it, and we have that vertical distance. you see, for that second graph. And for this x value, think about that vertical distance, and for the other graph, double it, and we get the vertical distance associated with this other graph. We can examine the transformation idea just by using function notation. For example, suppose we have a graph here, and without even using some equation to describe the graph, let's just say that it's the graph of f of x. Now, f of x means the same thing as y, and y is simply some vertical distance. That is, for every x, for example, this x value, there's a vertical distance y associated with it. And the graph is simply composed of a group of all vertical distances, all y values, working in concert to describe the behavior of the graph. Now, with that in mind, we can think about what it means to have f of x minus 3. It simply means all these y values down 3 on the coordinate plane. What about f of x minus 2? Well, there are really two ways of looking at this situation. X minus 2 means take all the x values, all the entire x-axis, for example, and move it a negative 2. Move it 2 units in the negative direction. And the graph then looks like this. Well, we usually don't think of moving the coordinate system, leaving the graph stable, you see, and moving the coordinate system. We would normally remember it in another way. We normally think of it as the graph moving in an unexpected direction, you see, left or right. And here the graph is simply moving to the right 2 units on the coordinate system. Well, let's put both ideas together. Let's think about horizontal and vertical movement. F of x plus 3 plus 2. Well, the x plus 3 means the graph moves left or right in a direction we don't expect, so the graph will move to the left 3 units. And the plus 2, of course, will move the graph up 2 units on the coordinate plane. Now, the negative of f of x simply means the negative of all of the vertical distances describing our graph. So any vertical distances that go up will go down, and any that go down will go up. So it simply causes the graph to reflect in the x-axis. Now, f of negative x causes a different kind of reflection. We can think of positive x's being swapped with negative 1s and negative 1s swapped with positive x's. And so, therefore, the graph reflects in the y-axis. The graph simply looks like this. Well, let's consider another kind of transformation. Let's consider what's called a non-rigid transformation. And non-rigid transformations occur when we have a coefficient of f of x that's other than 1. Here we have 1/2 f of x. By the way, the kinds of transformations before have been rigid transformations. We move the graph left, right, up, down, and we flip in a couple of directions, but essentially the graph maintains its fundamental behavior. Well, 1/2 f of x means all the y values we've been talking about are simply half as high or as low as they were before. So if we draw the graph from the y-axis to the left, it looks like this. And if I stop at some point, like this last point, you see this last point is simply half as high as its counterpart on the original graph. So we can continue. Now notice that the graph is simply taking on a rather squatty appearance. It's sort of fattening the graph in a way. Well, now let's put a number of the ideas together. Let's think about a number of transformations all in one kind of notation here. Now, the question might arise, where do we begin in a problem like this? And the safest thing to do is to begin within the parenthesis. Now, the x minus 3 will simply move the graph left or right in a direction we don't expect. We go to the right 3. Now let's think about what the outside 2 will do. Without the minus sign now, just the 2. It's 2 times all of those vertical distances. So we'll simply double all of the y values, and the graph will make an appearance something like this. You see, it'll simply stretch vertically. Now the negative on the 2 will simply cause all the y values to take on their negatives or their opposites, and it'll simply flip the graph in the x-axis. So the graph flips over like this. And of course the plus 2, the last plus 2 will move the graph up 2 on the coordinate plane. So here's our graph.